Okay, hello people. Um, yes, so this video will be a continuation of the previous one where I introduced you a concept of memory arenas and implemented it in C++. The problem with that implementation was that arenas couldn't grow. So, for example, if you run out of memory in arena, you just assert if you're trying to push a chunk which exceeds the size. And I don't know, and I don't remember whether I mentioned it before, but arenas can grow. So you can implement growable, or dynamically expanding arenas. So basically, the idea behind it is that when you run out of memory in the first arena or memory block, you make a call to an operating system, please allocate me an additional memory. So because I need it, I exhausted all the memory in the first one. And yes, so I modified the implementation a bit, and or I would say I completely rewritten it, and so we can go through it together. And I will explain what I've done, and I started to integrate a memory arena into a growing array. So we can take a look at the API as well, although it's not like fully ready, but it's close, and. Yeah, and I will put the code in the description as well, so we can take a look. I'm not sure whether I will merge it to master because it's on a separate branch. It's called Growing or Dynamic Arena prototype, but we'll see how it goes. And yeah, if you're interested, I've written the architecture document, and I've tried to explain how the arenas work here, and it is not complete, but at least it has some basic ideas, and you will be able to extrapolate some useful information out of it, right? So, and that is in the repo itself. Okay, yeah, let's go through the code. So nothing special. I still have a chunk, and which supports pushing operations, so we can push the data into the memory chunk. And basically, as I explained in the architecture manual, the arena as a whole, so I have three different abstractions. I have an arena, I have a chunk, and I have a memory block. And I have explained it thoroughly in the architecture document, so you can take a look. But I can go through it, and we can do it together. Maybe it's better to start from the arena itself, and then so we can go step by step, and from the high level to the low level. So the arena class, right? We still have an arena class, but it's not like a memory arena as I had before. It is rather a linked list of memory arenas, because I would have to solve a problem of running out of space in the one arena, so that if it happens, so I would have to reallocate. I would have to make a call to an operating system and ask it, please give me an additional memory, right? And this is what happens here. I just accumulate different memory blocks, and that is my arena. And this class contains the counter, which is SD, or it doesn't really matter. I could have written without SD, but I prefer prefixing this SD namespace. So it contains the amount of memory blocks that we have. And memory block is actually the memory allocated by the operating system. So for example, if we made 10 separate calls to the operating system, please allocate me memory, then the counter will be equal to 10. Right? And as I mentioned before, right now my arena is not a single block of memory. Right now it's a linked list of blocks of memory. So that is the difference. You have to keep it in mind. And it has basically an STD list, and there is an inherent problem here, and I will talk about it later a bit. But what I was trying to avoid, and I think I mentioned it in the architecture document, is that I was trying to avoid additional memory allocations. So for example, if I make a call to an operating system, please give me an additional block, I don't want to make any additional calls at all for maintaining this block. And I was trying to avoid it as much as I can, but here I couldn't come up with a great idea of how to do it. And unfortunately, I had to use as the list of uniquely pointers to memory blocks. And so this is our linked list, right? And I maintain a mutex because since the idea behind an arena is that it will be shared by multiple data structures, by multiple pieces of code which require memory. And some of them might request chunks concurrently, right? And I have to guarantee that the arena itself, the access to arena, is thread safe. So basically all the public API that we have here is thread safe. In each of these functions, I lock the mutex and I unlock it by the end of the functions, in the end of the function scope. And so this is like the only API that Arena has. It has a get chunk, which you've seen in the previous video if you watched it. And what it does is just gives you back a memory chunk. It takes the size, and actually I could have done it here as well. It gets the size and returns a chunk back, and it can take an old chunk, and in which case it would have to like free all the memory, not free, but put the old chunk into free state, so then can be reused by others, and it doesn't really free any memory, it just resets the chunk and sets the state of the chunk that basically marks it as available for someone else to pick up. And it has a release chunk, which basically releases the chunk, puts it in a free state. It has an empty chunks count, which is the amount of chunks that we have. But here, it's not like amount of chunks in a one memory block. It is rather the amount of chunks across all the memory blocks. Since Arena, the class Arena in my case, it's not a single memory block anymore. It is a linked list. So I have to, like, all the operations are designed with the consideration that we have to iterate over all the memory blocks, right? And this is like total blocks. It returns how many memory blocks we have in general, and total chunks, how many chunks across all the memory blocks we have in general. So I have a nested class here, memory block, and this is actually an abstraction around the memory block that our system has allocated. And it has a state, but this is like for the chunk state. And it has an additional structure, which is a chunk header. And I don't remember whether I've tried to explain it in the previous video, but what a chunk header is, what a chunk header does is just for any chunk that you request, instead of like, how should I explain it? So basically, memory block, inside a memory block, we have a linked list of chunks as well. And it is a doubly linked list because, and I would say even more, it is a circular double linked list. So this chunk header is a circular double linked list, and it has a chunk which can be of any size that the user requested. It has a chunk state, which can either be in use, which means that someone uses this chunk, or it can be free, which means that nobody is using this chunk and it is ready to be used by anyone else who requests the size that this chunk holds. and then we have a next, and then we have a pref, right? So we have a next and the previous pointers, and as I mentioned before, it is a circular doubly linked list, and basically each memory block maintains a pointer to all the chunks, and it is very important to distinguish that in this situation, I don't need any additional memory allocation to keep a linked list of chunks, whereas here I need a steady list to keep track of how many memory blocks I have, right? But here they point to memory itself, so I don't need to do anything. So we allocated a memory, and these chunk headers, they are stored in this memory. So then I just can work with pointers, and those pointers, they point to that memory that the memory block holds. It has a constructor which makes a call to an operating system, and probably I don't remember. I would have to go through it and make sure that some of them can throw exceptions, whereas some others can't, and mark no accept accordingly. I haven't done that yet. It just I spent a lot of time by modifying it, so I would have to document everything what we have here, right? So nothing has changed. I have a friend arena, so that arena can access some members, and then I have a position, capacity, total chunks, empty chunks, so nothing special, exactly as we had in the previous video. And then I have an std byte, which is a pointer to our data. It can be a void pointer, it can be a char pointer, it can be an unsigned char pointer, whatever you prefer. I just want to go with std byte, right? And then the API of the memory block. And I would like to mention that this is private. This is an implementation detail of an arena. That's why I have hidden everything. And chunk as well, like the chunk is a user-facing API. And again, you can always take a look at the architecture document, because I've tried to document everything and describe how it works, at least conceptually, maybe not given a lot of details, but as I go through this project, I will add more and more documentation, and it will be more self-contained. So coming back to a chunk is a user-facing API, right? User will be interacting with a chunk, and I can show you actually the growing array. So this is the growing array that I have been working on, and currently it uses my arena, right? So what it has is an arena, a pointer to a chunk, and I was thinking about how to combine those things together so we can operate only on one thing, but that will require an additional abstraction, right? For example, I don't know, a chunk manager or whatever, or maybe a memory struct which will hold an arena and a chunk. But I decided to keep them separate for now. And it has a size and it has a capacity. So like the regular implementation of the vector, except these two things, it has a pointer to the data. But in my case, it's an arena and a chunk. Right? And I made the constructor of the chunk be private, so that, and I marked that arena is a friend of this class, so only arena can create instances of this class. Otherwise, you cannot create instances of chunk somewhere else. You can create a pointer to it. You cannot create a reference, yes, but you cannot create an instance of this class. So here is the chunk, here is the chunk state, next, previous, that's it. New chunk creates a new chunk, free chunk puts the chunk into the free state, so basically changes the state to free, and get empty chunk searches, it iterates over all the chunks that we have inside this memory block, inside this linked list, doubly linked list, right? It iterates through all the chunks and it tries to find the one of an optimal size which fits our request the best, right? Total chunks just returns the number of chunks that we have. And this is probably, I don't know whether it can, probably it can't throw an exception. We'll take a look at the implementation shortly. So this is get empty chunk. It cannot. So free chunk, I don't think that it can. We can mark it as no accept, and then new chunk can be marked as no accept as well. Okay, so that's great. I've mentioned the API. It returns an optional. I don't remember whether I had an optional in the previous video or not. Let me quickly no, I would have to stash all the changes, but that's all right. Okay. Where I stopped. Okay, so here is the chunk that we return, right? Get empty chunk function searches for the most optimal chunk. It returns it if it was able to find it. So we return optional. If the optional contains a value, we operate on that chunk. If it doesn't, we create a new chunk, etc. Yes, so nothing special, and the chunk, it has like template functions for pushing the object. It does some checking whether the chunk fits or not, and then it has like a pop which decrements the size, and it has a begin and end, and remaining space is basically returns the number of bytes remaining in this current chunk, how many elements we can push, or how many bytes we can push more in order for this chunk to be full. Reset, I would recommend that as well. What a reset does is just resets the position of the chunk to be 0, and mem sets all the memory to 0, so we have a clear chunk that when the one data structure comes, or somebody else who will be using that chunk, it operates on a clear memory, on the like 0 initialized memory, and doesn't have any garbage. So it comes with a cost of 0 initializing the memory all the time. No, we put it inside a free state, but the benefit of it, it's way more easier first for debugging, and it prevents like any kinds of bugs. And here we can go through the implementation. So what I have is, I have an exception here. Yeah, and I don't know, I want to mention, but I'm using the external library. It's called FMT, and I will try to find the occurrences of FMT instead of using SDC out, which is, I find, like very convenient library, because you can like write a string and your data is here. Right, so instead of typing like %s, you can type like brackets, and then you put the data after. And yeah, and here actually I throw an exception, but we'll get back to it later. So I have an exception class, custom exception class, and it's in anonymous namespace. And anonymous namespace, what it means is that since it is in the CPP file, it means that this exception class is only visible to this translation unit, right? So nobody else will be able to nobody else will be able to access it outside. So yeah, exception, and I throw this exception if I fail to allocate memory, if the call to an operating system failed, and I inherit from an exception, and I just overload the constructor, and I bypass the message to an actual constructor of std exception. So that should be simple enough. Then I have an arena, I pass the size, and I create an instance of unique pointer which points to memory block, and that will initialize, call the constructor of the memory block, and which will actually make a call to an operating system in order to allocate memory, right? And then I insert that into the linked list of memory blocks, and I increment the count. So here it's because I want to mention as well that the arena is you cannot copy the arena, you cannot copy assign the arena, but you can you can move the arena, I guess. I hope so. Yes, okay. Because that was I was looking into memory block. Memory block is not copyable, neither movable. So the arena can be moved, but it cannot be copied. And this is what I'm implementing here. In just move constructor, move assignment operator, and we just shuffle on blocks. We move all the blocks, and the blocks count, and here we check whether VR itself who we're trying to assign. So basically I'm trying to prevent this situation, like arena, we have created the arena, and then I say arena, right? It doesn't make any sense. And we want to avoid that kind of situation. And that would be like std poof. Yeah, I modified a little bit, like the public API for getting the chunk. So in this case, we still compute the total size, taking into consideration the alignment, and what happens is that we will have to iterate over all the memory blocks that we have, and we will have to request on each memory block, okay, do we have an empty chunk which satisfies our size requirement? If we do, then we return that chunk. If we don't, we keep a pointer to a potential memory block that we check that does this memory block has sufficient amount of space in order for us to create a memory chunk. If it does, we put the current, we point potential, we make like the potential block point to the current block that we iterating over. So then, if we won't be able to get to find an empty chunk in any of those memory blocks, we would ask potential block, memory block, to create a new chunk for us. And we might end up in a situation where potential block is not found. And in that case, what happens is that we grow our memory arena. We make an additional call to an operating system, we append our memory block to the linked list, and we create a chunk, a new chunk inside this memory block, and we return the chunk. So this is basically how the memory arena grows, right? So let's imagine the situation that we were able to find an empty chunk of the requested size. And I don't know, like, I highly recommend watching the previous video because I explained thoroughly how the computation of a total size works, but I can go through it one more time. So basically, the size is always aligned by the page size, and the page size is 1 kilobyte. So no matter how many bytes you requested, it could be like 512 or 256. In that case, the total size would be 1 kilobyte, because this is like the size of the chunk that we are trying to request here, right? And we can provide an old chunk, but I will talk about it later. And here is actually where we lock the mutex, so it is thread safe. Right, we do the alignment, and then, as I explained, we iterate through all the memory blocks that we have. We invoke the get empty chunk operation. Get empty chunk. Here is the get empty chunk function. I will put it on the left hand side so we can see it clearly, and I will go through it briefly, but get empty chunk is a member of memory block, right? And what it does is iterates over all the chunks that we have inside this memory block, because you remember I mentioned that each memory block maintains a linked list of chunks. So basically those chunk headers, those are the nodes inside our memory blocks, inside our linked list. So we have to iterate it just the most, like, the simplest iteration over the linked list, and we check if the chunk has a free state and the size of the chunk satisfies our request, our size constraints. Then we say that, okay, we have found a chunk, but we don't stop an iteration, we continue, because we're trying to find the most optimal chunk, and that's why I have this section here. If we have already found the chunk and we continue the iteration, and we found the chunk which is more suitable for our size, which is because it doesn't make any sense really, for example, to grab the most like the first chunk that we found. For example, if we requested, I don't know, 1 kilobyte and we found a chunk of 1 gigabyte, it doesn't make sense to use that chunk. What we have to do is iterate through all the chunks, and if we couldn't find any of them, then yes, we will use that chunk instead. Yeah, so I check whether when do I need to break out of the loop, like a basic, again, because I'm iterating over the doubly linked list. And here I check if I found the chunk header. I change the state of the chunk header to be in use, and I decrement the counter, the amount of empty chunks that I have. So I just use -1, right? And then I return an std optional which contains the chunk itself, or a pointer to a chunk. So here I check, okay, does std optional has a value? If it does, then we return the pointer to a value, or in other words, we return a pointer to our chunk that we were able to find. So here is the chunk, so the user can use it however he wants. And if we didn't find it, we check if this memory block, the current memory block that we are iterating over, has has sufficient amount of space. We assign it to a potential block, so then later we can create a chunk inside that potential memory block. Hopefully it makes sense. And yeah, if we didn't find a potential block, what we have to do instead is we have to iterate, or we have to create a new memory block, and we basically compute the size of the new memory block. It either will be like a total size, it's a maximum of 2 of those, or default allocation size. And what a default allocation size is basically a 1 gigabyte. So we can, if we run out of space in one memory arena, which is 1 gigabyte, we just, or it could have been any other size which the user specified, right? We accumulate the memory blocks of size 1 gigabyte, for example. Or if total size is greater than 1 gigabyte, then that size will be allocated, and this can throw an exception. And yeah, so we create a memory block and we append it to the list, and I use insert so I can get an iterator to it, and then I assign the pointer to a potential block, and then I increment the amount of blocks that I have created. Later, what I do is I create a new chunk, and let me find this function. It should be somewhere here. Yes, so I call new chunk, and this is the size that I have specified, and I have covered it like in detail in the previous video, but I can go through it again. We cast the m pointer inside a memory block plus the position, and that would be our chunk header, because again, as I mentioned, all the chunk headers are stored inside its memory block, and it's just a linked list of them, right? And each points to one another, so that's how they form a linked list. We do some like computation. We compute, okay, so this is the start pointer, and the start pointer is where you will be actually allowed to push data into the chunk that have been allocated, and this is the chunk size, and we have to deduct the size of the chunk header itself, because this amount of space will be allocated for the chunk header, right? So however many bytes it occupies, like it can be like 24, or I don't remember, but we have like a pointer which would be 16 already, then we have a chunk data structure, and then we have a state, so it may be like I don't know, around 30 or even more. So we would have to deduct that size here, and then we create an instance of a chunk, and again we are allowed to do that because we have declared that arena is a friend of the chunk, and I don't know, probably no, I shouldn't move here because the chunk itself is just a plain data. It's just a couple of the pod types and the pointer, so we are allowed just to copy it like this. And then what I do is I set the state to be in use, and then here is actually I insert the newly created chunk header into the doubly linked list. And the reason why I have to maintain it as a doubly linked list is because the insertion is like this. I don't have to iterate through all the chunks that I have. What I can rather do is to use the next and the previous pointer, and this can be a bit tedious and complicated for like it might be overcomplicated basically, but the idea behind it is I wanted to avoid any additional memory allocations, for example for keeping SCD list, because it doesn't make any sense to maintain them. And this is how the insertion works. If m chunks points to some chunk already, which means that we have one or more nodes inside a double linked list, then we have to follow this insertion process. Otherwise, what we have to do is we have to initialize mchunk. So mchunk will point to the current chunk that we have created, and again, just a pointer cast. We operate on the raw memory that was allocated by the operating system, and we cast and we just cast the memory and to the chunk header, right? And reinterpret cast is a bit dangerous, but this is what you have to do if you are working as low level as this. And we update next and previous pointers to point to itself, because as I mentioned before, it is circular doubly linked list, which means that the last element points to the first, and the first element and the previous pointer of the first element. Okay, listen carefully. So the the previous pointer of the first element points to the last. The next pointer of the last element points to the first, and that's how they form a circle, and that's why the insertion operation is very cheap, and deletion will be cheap as well, and like deletion in the middle, but we don't need to delete because we keep all the chunks, we just modify the state. Maybe later we can come up with the idea, okay, maybe I can merge some chunks together, or I can free some chunk and use it as a part of I don't know, like there are multiple things that we can do here actually, and we returned like the pointer to a chunk, right? Arena. Okay, so we returned the pointer to a new chunk. That's all great, and we have to check. And I wasn't sure whether the arena itself should do something with an old chunk, because an old chunk is actually okay. Let me think. Let me think about it for a second. Yeah, so there are two options here. Either the chunk itself should reset its state, and the user itself has to like copy all the data between the old chunk and new chunk, or here we do it inside the arena. So if we provided the old chunk and it is not null pointer, which that would mean that we have to copy all the data from the old chunk into a new one, and this is a member function. So it will copy all the data to a new chunk, and then we free the chunk that the old one, right? And I can take a look at the free function, and what it does is basically the iteration over all the chunks inside a memory block, and we iterating over like all the things inside the memory block. And it is really important here that this chunk belongs to this memory block, because otherwise we wouldn't find it. So we iterate over like all the memory chunks, and if we have found it, we reset its state, we mark the state as being free, and we reset the chunk, we reset its position, and we zero initialize all the memory that it holds, all the like empty space that it holds, and then we increment the amount of empty chunks that we have. So the public API of the arena empty chunks count will give us the corresponding and correct amount of empty chunks, because this one has been freed, right? And it returns a boolean whether we have found a chunk or not. Yeah, I don't actually use like a return value, but I would have to think about it. Yeah, okay, anyway, and by the end we return the chunk. So yes, and there are some operations for releasing memory chunks, and obviously all of them include the log guard, so I have to log the mutex because this is the API of the arena itself. Right, so we release the chunk, we would have to first iterate over all the memory blocks, and inside those memory blocks we have to call free chunk. Okay, so this is actually where I used that value. It returns a boolean whether it was able to find the chunk or not. If we were able to free the chunk, then we return, and which means that that memory chunk was present in this memory block, that like the current memory block that we iterating over. If it's not, we continue iteration over the memory blocks until we find a chunk. Empty chunks count iterates over all the memory blocks and asks every memory blocks, how many empty chunks does it have, right? Because every memory block has a linked list inside of it, which keeps track of how should I say it? How many empty chunks it contains. Then we have like a total chunks, and we have total blocks. How many memory blocks do we have? And that's it. And here is a constructor of memory block. We just do some computation and we make a call to allocate memory. Inside, and here is the destructor. We check whether m pointer points to something and we release the memory. I think where we do the calls, yes. So here we do an actual call to operating system. If we couldn't allocate memory, we throw an exception, allocation error, and here is the error message that will be a part of an exception that we are trying to throw, right? Here is the release memory. I don't think that I need to throw an exception and that it can fail at all. I don't know really, but I would have to double check. So here is the constructor of a chunk, which can be as well only called by the arena. Here is the copy operator, and as I mentioned before, and I use it here. I use it copy, so this is like one of the places where I use it, but the user has to use it as well. And what happens in that, I check whether like the size of the current chunk is less than the size of the chunk that we are trying to copy data from. In that case, we have to throw an error, throw an exception, sorry, that length, I'm throwing the length error, but it can be out of range or it can be any custom exception, whatever. Destination chunk doesn't have enough space required, that amount of space I specified, right? And the same happens when we're trying to pop an element. We specify how many bytes do we want to decrement, and if the amount of bytes that we specify we want to decrement is greater than m position inside the current chunk, we throw an exception as well. Reset zeros the size of the chunk and sets m position to 0, and does feed is actually checks whether yeah, okay. It checks whether we have enough space in the chunk. If not, we throw an exception, and it is used inside the here. So if it doesn't fit, we throw an exception. Why an exception? Because we cannot overwrite the memory outside the chunk boundary, because there will be another chunk, right? Because it's a continuous memory. It is a continuous memory block. We cannot overwrite what is outside the space that our chunk reserves, because there might be another data from another data structure that uses a completely different chunk, and then we override the data, and then it's going to be really, really bad, and that's why I'm trying to avoid it as much as I can. So I think that's it. That covers the memory arena, and then I have added some tests, and I think I've covered like partially all the tests in the previous video, but I have added a couple more for example, thread safety. What I do here is I create a memory arena as well, and I try to like get chunks. So in total I create 50 chunks, and all of those chunks are created by multiple threads. So here I create a vector of threads, and I reserve basically, so I don't waste any memory inside the vector, right? So I declare upfront how much space I need, and here I iterate over thread count, and what I do is I push threads so I can join them later, right? into the vector. So I move them, and each thread takes the lambda, it takes the pointer to arena and then the index, and that index will be used to access this array of pointers to chunks, right? So I maintain the array of pointers to chunks, and I create a chunk, and then based on this index I insert the chunk into that array. And that's why I pass an index here. And then we iterate over all the elements inside this vector, and I call member function as the member function. And what it does is actually it captures the pointer to a member function, and then it can be called as so basically if I were to create another thread, and then I say okay, member function, and that would capture the join function, and then t join, right? And then what I could do is t join, and I can pass an instance, right, of the thread that I have created. So that's basically what it does. It captures the pointer, it's a pointer to a member function. Otherwise I would have to write lambda here, which takes an instance of a thread and calls join manually. So basically something like this. I would have to, so obviously const thread and then thread join, right? So this is what I would have to call, and oh, it's not const, because I cannot call join on a const object. But yeah, member function simplifies this job for us, right? And I verify that I have created 2 memory blocks. So in this case, what happens is that at some point we figure out, or rather the arena, because it's implementation detail, arena figures out that we run out of space. We have to make an additional call to an operating system, and that will be our additional memory block. Yeah, and that's why we increase like the amount of memory blocks. And here we verify that we have gotten 50 chunks in total, and the amount of empty chunks should be equal to 0. Okay. Here I clear the threads vector, and then I can reuse it, but this time I pass the release chunks function, and what it does, it iterates over all the chunks, all the chunks inside our array, and it releases one by one, right? And then I test it testing it using multiple threads, and then again I iterate over all the vector. I join all the threads to make sure that they have completed their work, and then I verify at the end that all chunks have been freed, that the amount of empty chunks that we have here is equal to thread count multiplied by thread count, or okay, I was actually wrong. We have 100 chunks in total created during this test and released as well. Then I have a couple more tests for the chunk itself. So what I do is I acquire a chunk, and then I trying to push some data into a chunk, and then it's the assertion that it's a dash test. So basically I make sure that this procedure throws this type of exception. So the populate chunk lambda function will try to push a lot of data into this chunk so that it runs out of memory, and that will trigger this particular let me show you this exception here, right? And yeah, here I checked that popping an element like an empty chunk throws an exception as well. Just very simple tests. Okay, I have 10 minutes, and I will try to go through the growing arena, like what I have done so far and where I am currently. So as I mentioned, not growing arena, but growing array. Sorry, it's been a long day. So how is it going with a growing array? Yes, I was writing it to use my memory arena, and it had simplified a lot of code here. It make it more robust, more readable. I would say I haven't gotten to the place where I implemented like arrays and insert procedures, but I was dealing with iterators recently and tried to make them work. Although I don't have like almost any validation here because like I only check whether object is a null pointer or not, and then I throw the invalid iterator error, and this is like the the exception that I create here, and it is inside the detail namespace, right? I'm not sure whether it's a great design decision to keep it inside a separate namespace. It can be part of the growing array, like a subclass which is private and nobody can use it, or yeah, we can use already defined exception from C++. There are like a lot of different options, but how the constructor would look like is you would have to pass an arena, right? You would have to forget about passing an initializer list, because apparently that wouldn't work. You cannot pass initializer list together with arena because that's just not possible. And then like some basic operations like copy assignment. This is copy assignment, move, move assignment, and then so it's not ready yet, but I have like a couple of tests here where I try to test like very basic functionality that we are able to create it, and that we are able to actually insert some elements into the vector, and that everything works fine, that we can pop and then we can clear the vector. So the basic functionality works correctly, and we can use this vector however we want. But for example, some functions are not implemented yet. And this is how the data looks like. And I think I've shown it before. So we have an arena and the chunk here instead of maintaining just a pointer to a data. At the end, I would like to mention that one more time that I have written like the architecture document, and I will add more things to it as I progress through this project. I will add like the documentation about growing array and other things that I'm adding, and so that it will be self-contained, but at least I've tried to explain my best. Maybe not my best, but I could have explained more, but still, there is a decent explanation about how arenas work currently, how they grow, and why do they need to grow, and what happens if we run out of space in one arena, how do we manage all the memory blocks that we have allocated. And as I mentioned earlier, we use linked list, so everything is documented here. I think I will be finishing for today because it have been like an hour since I've started, and I'm getting tired a bit from talking. Yeah, talking is not writing code. It's way more complicated, as it turns out. But yes, thank you for watching, and I really appreciate the fact that a lot of people were interested in the previous episode where I was talking about Arena. I'm glad that I was able to find people who are on the same page as I am. So thank you all of you for that. And have a good day.